Why do we believe our dreams have price tags? Do we owe the gods our lives, our vast...
Welcome to the Deep Dive. Today we're tackling a truly revolutionary idea.
Definitely groundbreaking.
It's a model from Fox that basically reimagines the very stuff our universe is made of.
Yeah, it gets pretty fundamental.
Forget the usual suspects. This theory suggests that space-time itself isn't, the bottom layer.
Exactly. It suggests space-time arises from something deeper.
Units of information.
Units of information, yeah. Think of it as our shortcut today, trying to get a handle on this really cutting-edge view of reality.
Okay, so we're going right down to the bedrock, you could say. Exploring this idea that space and time emerge from, this huge network of information units.
That's the core idea. It's a bit like realizing a photo on your screen isn't actually a continuous image.
Ah, right. It's made of pixels.
Exactly, individual pixels. This is kind of the cosmic equivalent.
Okay, let's unpack this foundation then. What are these fundamental units of information actually like? I mean, they're not just simple on-off switches, right?
Oh, not at all, no. Each unit in Fox's model has several key properties, and the crucial thing, they're quantized.
Quantized, meaning?
Meaning they come in discrete amounts. Take energy, for instance. It doesn't just flow continuously. It comes in specific packets, multiples of the smallest possible energy unit, the Planck energy.
So like steps, you can be on step 1 or step 2, but not step 1.5.
Precisely. Like Lego bricks, you can have 1 or 2 or 10, but never, half a brick.
Got it. So the main point here is, at the very smallest scale, energy isn't smooth. It's stepped. What about the other properties?
Well, spin, you can think of that as a kind of intrinsic angular momentum for the unit that's quantized, too.
Okay.
It only takes on specific fixed values measured in units related to the Planck constant. Again, it's like a dial that clicks firmly into place.
No smooth turning.
Right. Specific settings only.
And this is where it gets even more mind-bending, doesn't it? Because position itself is quantized.
Exactly. Position isn't continuous either. It exists on a discrete grid, defined by the Planck length, which is an incredibly tiny distance. So the big implication is that space itself at the very bottom isn't smooth.
It's pixelated?
Fundamentally discrete, yeah. Pixelated is a good analogy. Think about what that means for, location and distance.
That's, almost impossible to really picture. But okay, these units, they're not just floating around separately, are they? You mentioned entanglement.
Absolutely. Entanglement is key. It's like a dynamic connection between two units, a kind of link.
Instantaneous.
Well, that's the usual idea. The strength of this connection can vary, it changes over time, and it's what really weaves these building blocks together.
And each unit also carries an information state, like qubits.
In essence, yes. Each one carries quantum information. So yeah, like tiny quantum bits.
Okay.
Now, here's where it gets really interesting. How do all these things, these quantized units, discrete properties, entanglement, how do they actually give rise to the space-time we experience?
The smooth, continuous space-time we see around us.
Right. And even more surprisingly, maybe a space-time where the number of dimensions isn't always fixed at 4.
Variable dimensions. Okay, that still sounds like something straight out of science fiction.
It does, I know.
Yeah.
It emerges kind of logically from the model structure. It's surprising, but it follows. The key is this idea of a local space-time value.
Okay, what's that? How is this value determined at each point?
Well, it comes from the collective influence of all the information units, plus a little bit of quantum randomness thrown in.
So each unit contributes somehow, like it has a perception of that point in space.
That's a good way to put it, yeah. A perception or influence.
And how strong is that influence? Is it the same for all units? Like, does a nearby low-energy unit count the same as a distant high-energy one?
No, definitely not. There's a perception function that describes it. A unit's contribution depends on two main things. Its energy.
Higher energy means more influence.
Yes, and its distance to that point in space-time. But the influence drops off really fast with distance.
How fast?
Exponentially. With the square of the distance, relative to the Planck length. So nearby stuff matters way, way more.
Okay, that makes intuitive sense. Like, a light bulb seems dimmer the further away it is.
Yeah.
And you mentioned randomness, a fluctuation function.
Yes, exactly. At each of these discrete points, there's a tiny random quantum jitter. Just a bit of inherent fuzziness at that fundamental scale.
A little wiggle.
A little quantum wiggle, yeah. Drawn from a normal distribution centered around 0.
So, okay, let me see if I follow. You add up all the perceptions from all the units at a specific point, factor in this tiny quantum fluctuation, and that gives you the local space-time value for that point.
Yeah.
That's the basis of space-time in this model.
You got it. That's the foundation. Now, we also need to talk about entropy.
Disorder, right.
Right. It plays a really crucial role in how this whole system evolves. Fox's model actually has 2 types of entropy.
2 types.
First, there's conceptual entropy. This is tied to the energy and spin of the units. Think of it as a measure of disorder related to those properties. Higher energy, higher spin means more conceptual entropy.
Makes sense. And the second type?
That's information entropy, which is basically the standard Shannon entropy you might know from information theory.
Applied to the quantum information states.
Exactly. It measures the uncertainty in the quantum information the units are carrying, and the total entropy is just the sum of those 2, conceptual plus information.
Okay, so we have these fundamental units, their quantized properties, they create this local space-time value, and there's entropy measuring their disorder in information. How does this whole system change? How does it evolve over time?
Right, the dynamics. Well, an information unit state isn't static. It changes over discrete time steps.
Little jumps in time.
Yeah, tiny steps. And that evolution is guided by the local space-time value right where the unit is.
How? What makes it change?
There are a few ways. One is movement.
The units move around.
They do. Their position changes based on the gradient of the local space-time value.
The gradient, like the slope.
Yeah. Imagine the space-time value creates a landscape, like hills and valleys. The units tend to move towards the higher points, the peaks.
Okay, so they're attracted to regions of higher space-time value. What else happens?
They interact, they can exchange energy and spin with each other.
Like collisions?
Sort of, yeah. If they interact, one might gain energy, the other loses it.
Yeah.
And crucially, their entanglement can get updated during these interactions.
So the connections change too.
The connections evolve, yes. They're not just passive parts of space-time. They're actively shaping it and reacting within it.
And the information they carry, the qubits, does that change?
Oh, yes. The quantum information state evolves too. There's a quantum evolution operator, and that operator itself is influenced by the local space-time value.
Wow. So the information is dynamically linked to the geometry around it.
Exactly. It's all interconnected.
This is getting incredibly complex. A whole web of interacting information.
Right.
So how does this local space-time value actually translate into the geometry we know? And back to this wild idea, variable dimensions.
Okay, yeah. The geometry, that's determined by the local space-time value through something called a metric tensor.
A metric tensor, that's a mathematical tool, right, from relativity.
It is. You can think of it as the rule book or the code that defines distances and angles the shape of space-time right at that specific point.
And the local space-time value sets the rules in that rulebook.
Pretty much. Fox gives a simplified example just to illustrate. It shows how the local space-time value could directly adjust the components of this metric tensor.
Adjusting the metric tensor changes the geometry.
It changes the geometry. It warps it, stretches it, changes how distance works right there.
Yeah.
So if the LP value changes, the local shape of space changes.
And you said simplified example, meaning the real math is probably...
Oh, almost certainly much more complex. But the principle holds. The fundamental units influence the LP. The LP shapes the metric. The metric is the local geometry.
What about these metric singularities you mentioned earlier? If the local space-time value gets too extreme.
Right. If the absolute value of LP goes above some threshold, the metric becomes undefined, null. It breaks down.
Breaks down like a tear in space-time.
That's one way to think about it. It could represent fundamental boundaries or limits where our usual understanding of geometry just doesn't apply anymore.
Whoa. Could that be related to things like, I don't know, black hole centers or the Big Bang?
Those are definitely the kinds of extreme places where you might expect such conditions. It's speculative, but possible. And crucially, the number of dimensions.
Yes, the dimensions.
That number is extracted from the metric tensor. The math of the metric tells you how many dimensions you're dealing with locally.
So if the metric changes dramatically enough because LP is weird,
the effective number of dimensions at that point could change.
That is still the most
wow.
revolutionary part of this.
So in some patches of this fundamental network, we might actually have, say, 2 spatial dimensions, or 4, instead of the usual 3.
That is the implication, yeah. It would depend entirely on the local arrangement of the units and the resulting space-time value right there.
Amazing. Okay, one last piece maybe. How do these units connect? You said entanglement, but also distance.
Right. It's not just about physical closeness in the grid.
Because entanglement can link distant units.
Exactly. So the connection strength between any two units depends on both. How entangled are they, and how far apart are they in the grid?
So high entanglement can bridge large distances.
Precisely. Stronger entanglement means a stronger connection, even if they're far apart. Closer distance also means a stronger connection. Both factors play a role.
Okay, let me try and summarize this whole picture, see if I've got it.
Go for it.
We start with fundamental information units. They have quantized properties, energy, spin, position on a tiny grid.
Discrete property. They entangle with each other, they carry quantum information, their collective influence, their perceptions, plus some quantum fuzziness.
The fluctuation.
Creates a local space-time value at each grid point.
Yeah.
This LP value then dictates the local geometry, the shape of space, through a metric tensor.
Which defines distances and angles locally.
And this metric can potentially lead to variable dimensions, different numbers of dimensions in different places, or even singularities where geometry breaks down.
If LFP gets too large, yeah.
And all these units are actively evolving, moving, interacting, exchanging energy, updating entanglement, changing their information states, all based on this local space-time value and their connections.
That's a really excellent summary of the core ideas in Fox's model.
Sure.
It's a radical shift, isn't it? Instead of space-time being this fixed stage the universe plays out on.
It's an emergent thing itself.
It's an emergent phenomenon, arising from the really complex dance of these fundamental information units.
It completely flips our usual understanding. I mean, the idea that space-time, something that feels so fundamental, could just be a consequence of, well, information processing and entanglement at the very smallest scales. That's profound.
It really is. And it leaves you, the listener, with a pretty fundamental question to chew on, doesn't it?
Which is?
Could our familiar laws of physics, gravity, quantum mechanics, all of it, could they just be, at their deepest level, really complex expressions of how these little information units interact and evolve?
Like the rules of the universe are the rules of this information network.
Indeed. And what about those variable dimensions? What could that imply for the big cosmic mysteries we still haven't cracked, like dark matter, dark energy? Could they be related to regions with different dimensionality?
Deep questions, definitely. This whole deep dive into Fox's model, it really gives you a powerful new lens to look at the universe through. Thank you for walking us through this. It's fascinating and incredibly thought-provoking.
My pleasure. It's mind-bending stuff to think about.
And thank you for joining us as we explored this quantum frontier where information meets reality. We really encourage you to keep pondering these ideas and where they might lead.
For what is joy if we have no sorrow? And what is today without tomorrow? Yeah. If you're not present, the rest is hollow. We're no good, but we'll pay the price to follow. For the dark arts, you gotta have heart. You need faith to live.